Section: Introduction. In this section, we discuss how artificial intelligence, AI, is profoundly influencing society and is seen as a major force behind progress. However, we face a paradox. While AI systems are rapidly improving, the pace of AI research is limited by human cognitive abilities. This creates a bottleneck where innovation is restricted not by technology, but by our capacity to conduct research. This leads us to envision artificial superintelligence for AI research, ASI-ARCH, AI that can independently perform scientific research and create more advanced models. One of the toughest challenges in achieving ASI-ARCH is neural architecture discovery, which is crucial for AI development. Each significant advancement in AI capabilities, like image recognition or language understanding, has been linked to breakthroughs in model architecture. The shift from convolutional neural networks to transformers illustrates how new architectures can drive progress. Currently, a key challenge is to improve computational efficiency while keeping the models expressive. To explore this, we focus on attention-based architectures, which are both important and actively researched. We aim to move beyond traditional neural architecture search, NAS, which is limited to human-defined parameters. Our approach represents a shift from merely optimizing existing designs to innovating new ones. Previous NAS methods acted more like selection algorithms rather than creative agents, but we introduce ASI-ARCH, the first instance of ASI-ARCH in neural architecture discovery. By utilizing the advanced reasoning and coding abilities of modern large language models, ASI-ARCH can autonomously create new architectural ideas, implement them, and rigorously test their effectiveness. This marks a significant step in demonstrating AI's scientific superintelligence in architecture design. Similar to how AlphaGo's Move 37 revealed insights beyond human understanding, ASI-ARCH uncovers architectural principles that exceed human intuition. After running 1,773 autonomous experiments over 20,000 GPU hours, ASI-ARCH identified 106 new, state-of-the-art linear attention architectures. Importantly, we established the first empirical scaling law for scientific discovery, showing that architectural advancements can be scaled with computational resources, shifting research from being human-limited to computation scalable. Our main contributions include: 1. ASI-ARCH framework. We created the first demonstration of artificial superintelligence for AI research through a highly autonomous system that allows AI to independently conduct the entire research process in neural architecture discovery. 2. Emergent design intelligence. We identified new design patterns from AI-driven discovery, showcasing architectural intelligence that goes beyond human design and introduces new principles for attention mechanisms. 3. Computational scaling of discovery. We discovered 106 new linear attention architectures and established a scaling law for automated scientific breakthroughs, proving that research can progress with computational resources rather than just human expertise. We also open-source our entire framework, the discovered architectures, and cognitive traces to make AI-driven research accessible to all. In the following section, we explore the role of AI in advancing its own research. Initially, AI acted as a sophisticated assistant, helping with specific tasks while humans directed the research. Over time, AI has evolved into an AI scientist, capable of generating new hypotheses and research ideas independently. Recent frameworks, like AlphaEvolve, show AI's ability to navigate the research cycle with minimal human input. As human involvement decreases, AI's potential for self-optimization grows, exemplified by systems like Darwin-Gödel machines that can modify their own code and validate changes. Building on this, ASI-ARCH applies self-evolution principles to the complex field of neural architecture design, which presents greater challenges than previous self-improving systems due to its intricate experimental environment and vast search space. Our work represents a significant effort to push AI self-evolution in this demanding and impactful area. Section Summary. In this section, we discuss the transformative potential of artificial superintelligence for AI research, ASI-ARCH, which aims to overcome the limitations of human cognitive capacity by enabling AI systems to autonomously conduct scientific research, particularly in neural architecture discovery. We introduce ASI-ARCH, a pioneering framework that utilizes advanced reasoning capabilities to innovate and validate novel architectural designs, demonstrating that research progress can be scaled computationally rather than being constrained by human expertise. Section: Efficient Architecture. In this section, we discuss efficient architecture. The transformer architecture has been the leading choice for sequence modeling, but its attention complexity, which grows quadratically, has prompted us to explore alternatives that are more efficient. This has led to a variety of designs. Among these, sparse attention methods like native sparse attention use hierarchical strategies to speed up processing while keeping model performance intact. Additionally, we have identified three main families of models that operate in linear time: linear attention, which utilizes linearizing feature maps; state space models, such as Mamba, which use structured state transition matrices; and linear RNNs like RWKV, which feature matrix-valued recurrent states. We see a trend towards combining different model types, as seen in architectures like Jamba, which integrate various strengths. This shift has expanded our design options significantly, making the best architecture highly task-specific. While previous efforts have focused on manually crafting individual components, this can be a lengthy process, often taking months for experts to create a top-performing architecture. In contrast, ASI-ARCH offers a systematic way to explore this complex design space through automated collaboration among multiple agents, allowing us to discover innovative architectures that go beyond traditional boundaries. Our methodology involves a closed-loop system for discovering new architectures, organized into three main roles. The researcher module proposes new designs, the engineer module tests them in real-world settings, and the analyst module summarizes the results to gain insights. We store all experimental data in a central database, creating a lasting memory that informs our process. To ensure continuous improvement, we use an evolutionary strategy that allows the model to learn from its experiences. This includes a comprehensive fitness score that evaluates each new architecture and the ability to draw on both expert knowledge and past experiment analyses for future designs. Given the resource demands of this evolutionary approach, we implement a two-stage strategy. First, we explore broadly with smaller models to identify promising candidates, and then we validate these candidates with larger models to confirm their performance. Our fitness function is inspired by biological evolution, where fitness determines survival. We define a fitness function that decides which architectures thrive in our process. Previous methods often relied solely on quantitative metrics, which can lead to reward hacking, maximizing scores without improving architecture quality. We address this by adding qualitative assessments to our evaluation. Our composite fitness function considers both quantitative and qualitative aspects, assessing performance and design quality. For performance, we evaluate benchmark scores and loss compared to baseline architectures, applying a sigmoid transformation to highlight small improvements while limiting extreme values. For architectural quality, we use a separate language model to evaluate aspects like innovation, complexity, correctness, and convergence. This dual approach allows us to capture qualities that numbers alone cannot measure. The researcher module is the creative core of our system, proposing new architectures based on past experiences and human insights. We aim to achieve high-quality innovations while avoiding redundant explorations that waste resources. To select candidates, ASI-ARCH keeps a pool of the top 50 architectures from previous experiments. For each evolution step, we use a two-level sampling method. We randomly choose one parent architecture from the top 10 performers for modifications and select 4 reference architectures from positions 11 to 50 for diverse design inspiration. This approach ensures we build on successful designs while allowing for exploration of new ideas. The parent architecture is modified directly, while the reference architectures remain unchanged as examples of effective design patterns. Section Summary. In this section, we discuss the evolution of the transformer architecture and the emergence of subquadratic alternatives, particularly focusing on the ASI-ARCH framework, which automates architecture discovery through a collaborative system of researchers, engineers, and analysts. We emphasize the importance of a composite fitness function that combines both quantitative and qualitative assessments to guide the evolutionary process in developing novel and effective model architectures. Section: Model Design. In this section, we outline our model design and implementation process. Before we provide historical data to the researcher for the next evolution cycle, we first summarize the data. Each architecture in our database includes detailed information such as its motivation, implementation code, experimental results, and analysis. To keep the context manageable, we use a low-temperature language model to create brief summaries of the natural language parts for each historical architecture. These summaries are generated dynamically for each evolutionary cycle and are not stored, which introduces variations in how the same data is presented over time. This approach prevents the researcher from receiving repetitive context and encourages diverse design explorations. The combined summaries give the evolution model a manageable context and a fresh set of insights for the next design attempt. Regarding program implementation, we note that traditional methods often separate architectural design from code implementation, leading to an information gap. The implementation model only sees high-level motivations and misses the rich context of the original design, which can result in discrepancies between the intended architecture and the final code. We address this by using a single agent for both tasks. It proposes the architectural motivation with full context and then implements the corresponding code while keeping the design reasoning in mind. To ensure that each proposed architecture is novel and correctly implemented, we have a two-stage validation process. The first stage checks for similarity to avoid redundancy. When a new architecture is proposed, we extract its motivation and use an embedding-based search to find the 5 most similar historical motivations. A specialized language model then assesses whether the new proposal is genuinely innovative or just a variation of existing work. The second stage involves code-level sanity checks to prevent implementation flaws, such as ensuring the code does not exceed quadratic complexity and that masking is correctly implemented to avoid information leakage. If a proposal fails either check, it is rejected, and feedback is provided to prompt a rewrite. In the evaluation process, which determines the final fitness score, we conduct both quantitative evaluation in a real coding environment and qualitative scoring by a language model acting as a judge. The quantitative evaluation occurs in an interactive coding environment where the agent uses specific tools to train, modify code, and check error logs. A key feature of our approach is the self-revision mechanism. Unlike previous methods that discard architectures failing static analysis, our system requires the agent to correct its own mistakes. When a training run fails, we capture the error log and return it to the agent for analysis and revision. This iterative debugging continues until training is successful, ensuring that promising ideas are not discarded due to coding errors. Additionally, an automated quality assurance system monitors training logs in real time to identify inefficiencies and fundamental bugs, allowing us to terminate flawed runs promptly and conserve resources. After the quantitative evaluation, we use a language model to provide qualitative scoring. This scoring considers objective performance metrics, architectural complexity, computational efficiency, and the novelty of the proposed ideas, all compared to baseline models. To ensure consistency, we provide a detailed prompt and slightly increase the model's temperature to encourage more nuanced justifications for its scores. To drive the evolutionary process, we equip the agent with 2 knowledge sources for each design step: cognition from accumulated human expertise and analysis from the system's experimental history. We build a cognition-centered knowledge base by selecting nearly 100 key papers in linear attention and using a dedicated language model to extract distinct cognitions from each. Each cognition includes the applicable scenario, the proposed algorithm, and the historical context. We carefully design the prompt for the extraction model to ensure that the extracted content aligns with the problem analyses generated by our analyst module. In the final analysis stage, the analyst summarizes the shortcomings observed in the current experiment, which is then used to query our knowledge base for relevant cognitions. The retrieved content is stored for future reference, providing a targeted way for the researcher module to find solutions. Section Summary. In this section, we describe our model design process, which includes dynamic data summarization to provide diverse insights for architectural evolution, and a unified approach that integrates design motivation with code implementation to prevent discrepancies. We also outline a two-stage validation process for novelty and correctness, a robust self-revision mechanism during evaluation, and the creation of a cognition-centered knowledge base to enhance future design steps with accumulated expertise and experimental insights. Section: Contextual Analysis. In this section, we describe our contextual analysis and methodology. Our ASI-ARCH system generates insights through an analysis module powered by a large language model. This module receives comprehensive data from our current experiments, including performance metrics, training logs, and baseline model performances. To mimic an ablation study, we also provide data from related nodes in the phylogenetic tree, assuming they share structural similarities. This allows the agent to deduce the contributions of individual modules by comparing performance among these similar architectures. We archive the analysis to guide future design cycles. To ensure efficiency in architecture evaluation, we implement a two-stage exploration then verification strategy. We believe that a truly superior architecture should show its benefits across various settings. In the exploration stage, we use smaller models and efficient protocols to quickly identify a wide range of promising candidates that outperform a baseline. In the verification stage, we scale up these candidates for extensive training and validation against established baselines. This approach balances broad exploration with thorough validation. For our experiments, we use DeltaNet as our baseline. Our scoring system has three components. We focus on performance differences within 10% of the baseline, using a sigmoid function to map these differences into scores. Architectures with losses more than 10% below the baseline are discarded due to potential information leakage. For qualitative scoring, we use a scale where DeltaNet is the midpoint and gated DeltaNet is the upper reference, with an evaluator rating each architecture on a scale from 1 to 10. To speed up our discovery process, we run multiple search processes in parallel, supported by a cloud-based database that stores all historical results. This allows agents to share knowledge and request data. We manage this parallel exploration with a candidate pool update policy. Initially, we conduct 200 explorations without updates to encourage diverse architectural exploration. After this, we update the candidate pool every 50 new entries, ensuring stability and consistency during exploration. Our search process consists of two phases with different configurations. In the exploration stage, we limit model size to about 20 million parameters and train on 1 billion tokens, sampling only 500 examples per benchmark for efficiency. In the verification stage, we scale promising candidates to 400 million parameters and train them on 1 billion tokens for initial validation. The best models then undergo extensive training on a dataset of 15 billion tokens to evaluate their capabilities against strong baselines. To balance exploration efficiency with validation accuracy, we conducted 1,773 explorations using 20 million parameter models, consuming around 10,000 GPU hours. From these, we identified 1,350 promising candidates that outperformed DeltaNet. We then scaled these candidates to 340 million parameters and filtered out overly complex architectures, training about 400 models on 1 billion tokens. Among these, 106 achieved state-of-the-art results, all available on our Model Gallery website. For final validation, we selected 5 top-performing architectures, training them at 340 million parameters on 15 billion tokens and comparing them against DeltaNet, gated DeltaNet, and Mamba 2. Our models outperformed nearly all baselines across various benchmarks. The 5 architectures we selected for final validation each represent unique strategies for enhancing the DeltaNet baseline. PathGate FusionNet introduces a hierarchical router for balancing local and global reasoning. Content Sharp Router creates a content-aware gate that makes sharp routing decisions. Fusion-gated FurNet changes the gating mechanism to allow simultaneous activation of local and global paths. Higher gate net uses dynamic floors for routing decisions to ensure critical pathways remain active. Finally, ADA multi-path gate net provides fine-grained control over paths while preventing gate collapse. Section Summary. In this section, we describe our methodology for architecture evaluation, which includes a two-stage exploration then verification strategy to efficiently identify and validate promising models. We also outline our scoring system, parallel search architecture, and the final selection of 5 innovative architectures that outperform the baseline, each employing unique gating mechanisms to enhance performance. Section: Effectiveness of LLM-driven architecture search. In this section, we demonstrate the effectiveness of our LLM-driven neural architecture search system by examining how the search process evolves over time. Our system selects parent architectures exclusively from the top 50 candidates, meaning the characteristics of this pool significantly influence the search trajectory and final performance. We analyze 2 main sets of metrics related to this candidate pool. First, the overall trend of the average fitness score for the top 50 candidates, along with the individual trends of its 3 components: loss improvement, benchmark improvement, and the LLM judge score. Second, the average raw performance, specifically the benchmark scores and loss values of these candidates. Together, these metrics give us a comprehensive view of our system's search dynamics and ongoing optimization. Our analysis reveals several complementary patterns. The average fitness score of the top 50 candidates follows a typical learning curve, showing rapid initial gains that eventually stabilize. The early increase in scores is mainly due to optimizing the loss component. The stabilization occurs because of our fitness functions design. The sigmoid transformation means that even significant performance improvements later on result in smaller score increases. This design prevents reward hacking by limiting the score contribution from any single metric, discouraging over-optimization. Importantly, while the growth of the fitness score flattens, we do not hit a performance bottleneck, as shown by the steady improvement in the raw benchmark and loss metrics. This evidence confirms that our LLM-driven search effectively learns to generate better architectures throughout the process. In our discussion of future work, we highlight that our framework successfully demonstrates AI self-optimization, where an autonomous agent can iteratively discover and refine new neural architectures. Our main goal was to prove that AI can navigate a complex design space to achieve state-of-the-art performance, and our findings suggest several promising directions for future research. One potential direction is multi-architecture initialization. Currently, we start the search from a single strong baseline, DeltaNet, which provides a clear objective and stable foundation for early improvements. An exciting extension would be to initialize the process with a diverse set of architectures at once. This could test the framework's ability to handle a more complex, multimodal search and might lead to discovering entirely new families of architectures, although it would require significantly more computational resources and time. Another avenue for future work is component-wise analysis. Our experiments confirm the effectiveness of our pipeline as a whole, but due to the substantial resources needed for each design iteration, we did not conduct a detailed study to isolate the contribution of each component. A crucial next step is to dissect the pipeline from various angles to better understand the interactions and individual importance of its parts, such as the cognition and analysis modules. This could enable more targeted optimization of the framework, potentially enhancing its efficiency and creativity.